Okay, welcome to the deep dive, the place where we take your sources and really dig into the important stuff just for you. Today, we're looking at the material you shared about Grevm 1.0.
That's right. We've got the archive gravity docs here for Grevm 1.0. It covers, the core concepts, the build, test results, and kind of where it's all heading.
So, Grevm 1.0, the source describes it as a high-performance parallel EVM runtime. Our mission today is to unpack all this, really understand the tech approach, see how it performed in tests.
Right, and get a handle on its limitations, too, because it was a proof of concept.
Exactly, and then see what's planned for Grevm 2.0. Okay, let's jump in.
So at its heart, Grevm 1.0 is presented as this open-source parallel EVM runtime. It's built on Grevm, which lots of people use. The main goal, tackling Ethereum scaling by running transactions side by side.
Okay, running things in parallel. And the docs say it pulls inspiration from the BlockSTM algorithm, but there's a twist.
Yeah, a pretty important one. They use transaction dependency graphs that come from simulation results. It's not just figuring out dependencies as they execute.
Ah, okay, so BlockSTM typically runs things optimistically, right? Then fixes conflicts. Grevm tries to get ahead of that.
Exactly. It simulates first, gets these predicted dependencies, and uses that to schedule transactions better. The hope is fewer conflicts, fewer re-executions, which are, costly.
And they make a pretty big claim based on this approach, right? Something about being the fastest.
They do. The source benchmarks it as the, quote, fastest open-source parallel EVM implementation to date. For transactions that can run totally in parallel, no conflicts. They hit 4.13 times faster than just running them one by one.
4.13x and the throughput figure.
Yeah, 26.5 zeros per second. And gigas per second, just to clarify for you, is basically a measure of the total compute work done. So 26.50 is, well, pretty substantial for that ideal conflict-free scenario.
But conflict-free isn't always the real world. The source talks about I/O latency, like database lookups.
Right, and this is where it gets really interesting. They simulate that delay, that time waiting for data, with just 100 microseconds of simulated database latency. The speed up compared to sequential jumps massively.
How much?
50.84 times faster. Now, the absolute throughput drops a bit, the 6.80 gigas per second, but that relative speed up is, huge.
Wow, 50 times faster just by adding a tiny bit of simulated wait time. How does that work?
Well, think about sequential execution. It hits a database read and it just stops,
Right.
waits. But a parallel system like Grevm, it's juggling multiple transactions. While one is waiting for the database, others can be computing or maybe starting their own database request.
Ah, so it overlaps the waiting time. The parallelism hides the latency penalty.
Precisely. That asynchronous I/O capability, unlocked because things are running in parallel, makes that latency almost disappear from the total block processing time. It turns a bottleneck into, well, less of one.
That's a really powerful idea. The thing that slows down old systems becomes an opportunity for parallel ones.
Exactly. And this isn't just some theoretical exercise. The source positions Grevm as a key piece of the bigger Gravity chain and Gravity SDK.
Right, their open source layer 1 toolkit, aiming for that 1 gigazis per second total throughput goal for Web3 scaling.
Yeah, a really ambitious target. They're also quite clear they're building on the shoulders of giants. They mentioned Grevm, BlockSTM itself, Aptos's work, other parallel EVM explorations.
Good to see the acknowledgement. And they're upfront that this Grevm 1.0 is a proof of concept, a POC. It has known limitations.
Definitely, they state that clearly. Grevm 2.0 was the planned next step to tackle those issues, and the docs say it was coming soon after December 2024. So we're looking at the first step, the validation phase.
Okay, great setup. Let's get into the technical design. The source mentions ideal parallel execution. What's the perfect world they're aiming for?
Right, so the ideal case, like in their figure 1,
Yeah.
imagine you could process all transactions at once with zero conflicts, maximum possible speed.
How would that ideal system know what can run together?
It would need perfect, instantaneous dependency analysis, like having a flawless map, a directed acyclic graph or DAG, showing exactly who needs what from whom. The example they use is good. TX3 reads Alice's balance, TX2 writes to it. TX3 must wait for TX2. You need that map.
Makes sense. You need to know the order for things that touch the same data.
Then you distribute the work from that map perfectly across all your CPU threads, balance the computation and the data fetching. You'd use this really efficient memory system like software transactional memory, so transactions can see the updates from earlier ones.
And if two transactions write to the same spot?
The ideal system just knows the final value is whatever the last transaction in the original sequence wrote. No confusion.
Okay, sounds amazing, theoretically. But the source says achieving this in real time, like when a block actually arrives, is super hard. Why?
Well, how do you get that perfect map, the DAG, without just running everything sequentially first? That's the core problem, especially with complex smart contracts like DAG swaps. You don't always know exactly what state they'll touch until they actually run. And trying to figure out those exact dependencies perfectly on the fly is computationally really expensive. It can add so much overhead, it cancels out the parallel speedup you were hoping for.
So predicting the interactions perfectly is too slow, but just running sequentially is what you want to beat. A bit of a catch-22.
Exactly. And that's where Grevm's pragmatic solution comes in, using those simulation results we talked about earlier.
Ah, the hints. Simulating first to get estimated read-write sets before the main parallel run.
Yes. These hints aren't guaranteed to be perfect, but the source argues they're generally accurate enough, especially for common stuff like simple Ether or ERC20 transfers make up, 55–60% of Ethereum mainnet transactions, and for those, simulation is usually spot on.
Okay, so it's a trade-off. Use pretty good, cheap-to-get hints from simulation to guide parallel execution, instead of aiming for perfect but expensive real-time analysis.
That's the core idea, and they structure this using a three-phase framework, kind of building on block STM.
What are the phases?
Phase 1 is hint generation and state preloading. That's the simulation part. Get the hints, the estimated read-write sets, and also preload needed state data into cache, warm it up. They suggest this could maybe even happen earlier, like processing from the mempool.
Okay, prep work. Phase 2.
Dependency analysis. Take the hints, build that dependency DAG based on them. This map then tells the scheduler how to group and order things for Phase 3.
Build the plan based on hints. And Phase 3.
Concurrent execution with conflict resolution. Now you actually run the transactions in parallel, guided by that DAG from Phase 2, trying to minimize clashes. It uses a modified block SPM approach. After running, it checks everything, validates the results.
And what if the hints were wrong and there are conflicts?
That's where it gets iterative in the 1.0 PC. The validation step sorts transactions. Finalized or good to go. Unconfirmed might be okay but need checking. Conflict definitely need rerunning. If not, everything is finalized.
You loop back.
Right. You can take the actual read-write sets from the round you just ran, which are now better hints, and feed them back into the process, starting again from Phase 1. They allowed up to 3 rounds in the PAPO. If it's still not resolved after 3 tries,
Then what?
fall back to sequential execution for whatever's left. Slow, but safe.
Okay, that loop seems like a way to recover if the initial guesses were off. Now let's talk about the Grevm 1.0 implementation itself, the PAPO figure 2. What choices did they make there?
Yeah, for 1.0, the goal was validate the core ideas, hints, parallel framework, but keep the engineering simple. So some compromises were made.
Such as?
In the dependency analysis phase, after building the DAG, they grouped transactions into these things called weakly connected components, or WCCs, basically clumps of transactions linked by dependencies. Then simple algorithm tries to split these WCCs across the CPU threads, trying to balance the work.
So break the block into these connected groups, assign groups to threads.
Correct. But here's the crucial simplification in 1.0. While different WCCC partitions run in parallel with each other, all the transactions inside a single WCC partition are executed sequentially, one after another.
Whoa, wait, so even if 2 transactions in the same WCC don't directly depend on each other, just being in the same group forces them into a sequential line within that partition in 1.0.
Exactly that. And this leads straight to a major known limitation of the 1.0 POC, which the source is very open about. This WCC partitioning is called overly restrictive. It treats any dependency link within the group as forcing sequential execution for the whole group.
And the result of that restriction?
Well, imagine you have high contention, lots of transactions hitting the same few contracts. This approach can lump a huge chunk of transactions into one single massive WCC. The example given is at a 30% hot ratio, maybe half the transactions end up in one big group.
Then since that group runs sequentially,
Your parallelism tanks. You end up bottlenecked by this one long sequential process running on one thread, even if you have tons of cores sitting idle. It really limits the potential speed up when contention is high.
that makes perfect sense. A bottleneck created by the grouping strategy itself. Any other key limitations mentioned for 1.0?
The other main one relates back to the hints. If the simulation hints for complex transactions are quite inaccurate, the system might fail to sort out the conflicts even after the 3 iterative rounds. Then it falls back to sequential. In some really bad cases, this fallback could actually make Grevm 1.0 perform worse than something like standard block STM.
Okay, so the WCC grouping under contention and hint accuracy are the key watchouts for 1.0. How did this actually look in their evaluation? What tests did they run?
They used a standard cloud VM setup, detailed in the source, and ran the gigas block test. That simulates processing a 1 gigas block with different transaction types. And crucially, they could add that artificial database latency using a parameter.
They started with conflict-free transactions, the ideal case, right? No dependencies.
Correct. Symbol ether transfers, separate ERC20s, isolated Uniswap pairs, designed purely to test the maximum possible parallel speedup without worrying about conflicts.
And those are the numbers we saw earlier, the 4.13x without latency.
And that massive 50x plus speedup with the 100 microseconds of I/O latency.
Yeah.
Table 1, Figure 3. For raw transfers, 50.84x, ERC20, 50.87x, Uniswap, even higher at 58.06x.
It really drives home that point about overlapping I/O.
Absolutely. Sequential just waits. Parallel Grevm keeps working. It shows how parallel architectures can really thrive when dealing with state access delays, at least in this kind of setup.
Very compelling. How did it compare to PEVM, which is like a standard block STM that was in Table 2?
Yeah, conflict-free, no latency. Pretty similar performance. Both are parallel, both use multi-version state, but add latency. Grevm 1.0's async I/O handling gave it, quote, significantly superior performance.
Except for Uniswap. The source noted Grevm was slower there with latency in that comparison.
Ah, yeah, good catch. That was traced back to the 1.0 PC's implementation details. Merging the state changes back together after the parallel execution was still quite sequential and involved a lot of data copying. For complex transactions like Uniswap that touch lots of state, this became a bottleneck. It's flagged as something to fix in 2.0.
Got it. An implementation artifact of the POC. They also had end-to-end figures in Table 3, including some overheads.
Right. Things like bundling the final state changes. Even including those, the overall speedup was still considerably significant, especially with that database latency factored in. The core parallel benefit wasn't lost.
Okay, conflict-free looks good, especially with I/O weights. But the real test is contention. That's the hot ratio stuff.
Exactly. They set up a scenario with some hot accounts that are accessed frequently. Table 4. The hot ratio is the probability a transaction hits one of these hot accounts. They tested with a mix of transaction types at 0%, 10%, and 30% hot ratios.
What did those results show? Tables 5, 6, 7, figures 4, and 5.
Well, a 0% hot ratio, basically, uniform workload, no specific contention. Grevm 1.0 still did really well. Significant speedups compared to sequential, like 1.43x without latency, 7.73x with the 100 EDOS latency for their hybrid mix.
But then the hot ratio went up,
And performance gains dropped off, especially at that 30% level.
confirming the WCC limitation we talked about.
Precisely. At 30% hot ratio, the math shows there's a high chance transactions link up through those hot accounts. So you get that big single WCC forming, grouping maybe half the transactions.
And that big WCC runs sequentially in 1.0.
So your parallelism is crippled. It becomes bottlenecked by that long sequential tail. The evaluation data clearly shows this 1.0 design limitation biting under high contention.
So Grevm 1.0 proved the concept, showed big wins against I/O latency, but hit that wall with contention because of the simplified WCC handling. Where next? The future work section.
Yep. They mentioned wanting to do more analysis, look at memory usage, DOS risks, really compare re-execution counts and CPU use against others. They expect Grevm's hints should lead to fewer re-executions. Also, analyzing hint accuracy more deeply, false positives, false negatives, and their real impact.
And then Grevm 2.0, Figure 5 references it. This is where they fix the 1.0 problems.
That's the plan.
Yeah.
Two main enhancements highlighted for 2.0 to tackle the 1.0 bottlenecks. First, finer-grained transaction-level concurrency. This directly targets that WCC problem.
How?
The goal is to allow transactions within the same WCC to run in parallel if they aren't directly dependent, even if they're distantly linked, unlocking more parallelism, especially for those high contention workloads that choked 1.0.
Okay, breaking down this sequential execution inside those big groups. What's the second enhancement?
Fully asynchronous I/O. While 1.0 demonstrated the benefit, 2.0 aims for true async I/O across the whole system, database, state memory, everything. Should make it even more efficient, cut down context switches, and squeeze out more performance from data access.
Okay, let's wrap this deep dive on the Grevm 1.0 sources. We've seen it's a really promising proof of concept, showed major speedups over sequential.
Especially highlighting how parallelism helps deal with real-world things like I/O latency, thanks to that asynchronous overlap capability.
But we also saw its key weakness in this first version, clearly identified in the source and the tests. That WCC partitioning strategy really limited performance when there was a lot of contention, forcing too much work back into a sequential line.
Right, and the path forward described is Grevm 2.0, specifically designed to smash those bottlenecks with more granular concurrency and fully async I/O, pushing towards that big gravity chain performance goal.
It's a classic engineering story, isn't it?
Mm,
Build a PAC, prove the idea works, find the practical limits, then design the next version to overcome them.
absolutely. A clear progression.
It really is. Okay, as we finish up, here's something for you, our listener, to think about. Grevm's whole approach hinges on using those simulation hints before execution to guide parallelism. So, how much might the inherent limits on how accurately you can predict complex contract behavior before running it fundamentally cap the maximum speedup any parallel EVM design like this can achieve? It's a fascinating trade-off to consider in the quest for blockchain scalability,